Hi, I'm Brian from Simply Brian Enterprises and welcome to my channel. In today's video, we're going to keep looking at the non-homework solution for lesson number 18 of TopTechBoy's Raspberry Pi class. If you remember in my last video, I left off after writing some programs against the joystick, talking about a flaw in my program, and so that's where I want to pick it up today. I want to look at that a little closer and start to evaluate a potential solution for this problem. So first of all, we have to understand what's going on with the program, why there's a problem in the first place. So I'm going to go ahead and I'm going to run the very first program from last video, which is just taking numeric input from the joystick. You can see I'm moving it around in the XY axis, pressing the button. Everything looks fine, right? Well, so what's the problem? Well, the first problem is something that Keith had mentioned in a comment in my lesson 16 video. When I hold down the cat talk button, it stops all code execution. You notice that while I'm holding that down, nothing is happening until I release it. And there's strike two. You also notice, oh, did you see that? I just pressed the cat talk button and nothing happened. I pressed it again and something happened, but shouldn't it read that button every single time? What's going on there? Well, let's take a look at the code and see if we can understand where the problem lies and what kind of design mistakes I made, and then of course we'll look at potential solutions for them. So the first thing we'll look at is, why does code execution stop when I hold down the cat talk button? Well, if we look at the actual code for this, we're processing the button. It's a pull up button, so when it's false, that means it's pressed down. And as it's pressed down, we're in this while loop, and the only thing we're doing is we're sleeping for 10 milliseconds. Now, of course, that's a perpetual loop, so it's not just 10 milliseconds and move on. It's 10 milliseconds, loop back, another 10 milliseconds, and we're just in this perpetual loop where we're doing nothing but sleeping. So that's why all code execution stops, because when I'm holding the button down, nothing else is happening. So why is it that sometimes when I press the cat talk button, nothing happens? Well, because there's another sleep loop, and this sleep loop is in here to make the joystick operation smoother, moving left to right. And as I'm doing that, I don't want the value to increment too quickly. I want to slow it down. So I have a 200 millisecond delay in there. Well, the problem is that I have a perpetual while loop, looping around, looping around, looping around, waiting for input from the joystick, waiting for input from the cat talk button. And every single time through the loop, there's a 200 millisecond wait. So if I press this cat talk button while we're in this sleep loop, it's never going to read the input value. So there, right there, because we're using sleep, is actually preventing the program from reading our inputs or running the program at all in the case of holding down the button. So to illustrate this problem a little better, I'm going to actually switch back over to Arduino, and I'm going to run a small program I've written because I can illustrate this same problem in the Arduino world and also talk about potential solutions, maybe a little bit simpler using the Arduino IDE. So here I have a simple program, and what I'm doing here, let's flip over to just the table camera so you can see what's going on. So I have a potentiometer wired up, and I have a flashing LED. And as I turn the potentiometer to the right, it flashes faster. And as I turn it to the left, it flashes slower. Seems like a simple program, right? Okay, well, what happens if I go all the way to the left? Okay, there's my slowest. Now I'm blinking about once per second on and off. Well, what happens if I quickly turn that up? Look at how quickly it took to read the new value, because now it's sitting at about 300 milliseconds, but you notice it was blink on for a second, blink off for a second, then move into that 300 millisecond blink rate. So what's going on there? Looks kind of like the same problem I just explained in my Pi program. So let's take a look at the code and see if we can understand this a little better. So what I'm doing is I'm reading in the potentiometer value, and then I'm doing a simple invert. So I'm taking 1024 minus the input value. So when I'm all the way to the left, my A0 value is 0. Well, I want that to be a longer delay, so I'm going to say 1024 minus 0. So now my delay time is 1024 milliseconds. Whereas if I turn it all the way to the right, it's now 1023. Well, 1024 minus 1023 is a delay of 1 millisecond. And as you can see on camera here, it's basically blinking so fast that you can't tell it's blinking at all. It looks like it's just solid on. So that's a pretty straightforward program. Well, it would be if the redabbler wasn't sliding away from me. Here we go. But do we see the problem here? After I read in the value and invert it, I set the pin to high, the onboard LED pin to high. I sleep or delay for that length of time, set it to low, so I blink it off, and then delay again. And then I come all the way back up here to reread the potentiometer value. So that way, if this is all the way to the left, and I turn it all the way to the right, well, the problem is it's still in those delay loops. It's going to have to execute all those delays before it can get back up and reread the potentiometer value. So again, we have kind of the same problem we have on the Pi program, where we have to stop program execution to do something to make something look proper. In this case, blink the LED at the proper rate. But then when we do that, we're stopping input. So we're not reading the potentiometer as input, which when we start to add more inputs like temperature sensors and we add more outputs like LCD displays, that's a problem. We can't be stopping the code in between reads. We want to be reading those constantly, even though we may be waiting for user input, a push button or a potentiometer or something like that. So how do we solve this on the Arduino? Well, on the Arduino, we use a function called millis. And what millis does is it is an uptime counter of how long the board has been powered on. A power cycle, executing the program code, or physically pressing the reset is going to set the millis counter back to 0, and then it's just going to increment how many milliseconds the board has been powered on. And this number is stored as a 32-bit long integer, and it will eventually max out and roll over at 49.7 days. Now, as a hobbyist, my code is rarely running that long on an Arduino, but if you're building something that's going to be part of another circuit or another project that is intended for long-term use, that becomes a real problem. You have to account for that. So when we're setting up our variables to handle millis, we're going to use a long integer because we can't use a 16-bit. That's too short. We'll run into trouble. So we have to use a full 32-bit integer. And we also want it to be unsigned. That way, when we do subtraction on it, we still get the proper difference, and you'll see why that matters as we move forward. So here I have essentially the same program, and I'm just reading my potentiometer, inverting the value, setting the onboard LED to high, doing a delay of that delay time that we calculated from the potentiometer. But then I come down here, and instead of using a delay function, I've written my own delay function using millis in hopes that this can kind of illustrate what's going on. So the first thing we want to do is we want to catch the current time of millis and set it to a value, in this case current millis. That's just, we're running the program, what is our current uptime in milliseconds? Then we want a value that does not change called previous millis, or I should say that we only set when we really want to, called previous millis, and in this case we're going to grab the current time as well. Now we're going to head into this while loop, and we're going to take the current milliseconds, subtract our saved value in previous milliseconds, and compare it to delay time. In this case, we're going to come through here, so we'll get a value. We'll get the same value. We come here, this value is 0, less than delay time. Okay, so we're going to run this loop, and all we're going to do is check the current time, and then loop back again. So eventually this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 milliseconds, all the way up until that delay timer expires. Once that delay timer expires, then we can go back up and then we can reread the potentiometer. So this program is going to work exactly like the one I just showed, but instead of doing a delay function, instead of using the built-in delay function, I've written my own using millis to kind of demonstrate how millis works. Now, why would I do something like that? Well, In this case, I'm just doing a simple delay. I'm just looping, checking the time, checking the time, checking the time. Has my timer expired? Has my timer expired? But what I can also do is expand this function out, and I can put more code in here. I'm not just checking the time. What if I do other things? What if I check the input of the potentiometer? What if I check the input of a joystick? And so we have such code, and I'm going to go ahead and execute this. I don't know why that's highlighted. And I'm going to execute this. Again, my potentiometer is halfway up. And so this time, we're going to flip over to the table view again. And now I'm going to go all the way to the left. So we saw that before, right, where we got that slow blink. Now I'm going to turn all the way to the right. Notice how quickly that responded. As soon as I turned it, the delay timer changed. The delay timer changes exactly with the movement of the potentiometer. There's no waiting. There's no stopping in the code. So what's going on? Let's take a look at the code and see if we can understand why this is different than the delay code that I just showed you. So I'm coming up here again and setting my delay time, my previous millis. I'm using a state value this time, a Boolean state of LED false or LED true. Of course, false is off, true is on. And so I'm coming down here, setting up the onboard LED, setting the default state to false, LED off. Then what I'm going to do is I'm going to, every time through our perpetual loop in Arduino, I'm going to read the current timestamp in millis. Then I'm going to read the potentiometer value and do the invert. Now I'm going to check the current timestamp against the one we previously stored. Now to start with, we use 0, and of course that's going to expire right away. So in this case, we're going to hit a true here right away and head into this if, and we're just going to flip the bit to on. But then we're also going to reset our previous saved value. So the way this is going to work, we're coming in and we are grabbing the current time, reading the potentiometer value, flipping it, and then we're checking that current time against the time that we stored previously. And we say, okay, is it, excuse me, is it greater than the delay time? No? Okay. Well, then we're going to skip this if, and we're just going to keep going. Oh, and I should point out, every single time we go through the loop, we're writing out the state. This is important because you'll see once that timer expires, we come into this if loop. Oh, now current millis is greater than our stored value, or our current time minus the stored value is greater than our delay time. So we triggered that delay, we've expired the timer, now we need to make a change. We're going to flip that state, we're going to reset the previous value, and this is important, we're just flipping the state. We're saying false becomes true, true becomes false, and then we're going to write that out when we get here. Now, false has been set to true, previous millis has been set to current millis. We go back up into the loop, we do this comparison. Okay, nope, still 0, so we don't make a change, and we're going to write it out. That value is still true. And it's true, 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 true until the timer expires, and then we flip it to false, reset the timer, write it out false, and on and on and on. And we do this perpetually. The key here is we never stop the code. The code is running constantly. We're not pausing to wait for user input. We're not pausing to blink the LED. We're not pausing to do anything. We're reading constantly. And the reason we're going to do that is because if we have multiple inputs and multiple outputs, we don't want to stop the code for anything. Now, what would happen if we did have multiple inputs and multiple outputs? Could we simulate something like that? Oh, well, I think we just might. So bear with me. This is live television. Never know what's going to happen exactly. And I've got my little cheat sheet here to wire this up quickly. We'll see if I can do this on camera. And I'm going to try to get these pins in the correct order. See if we got this here. So I've got my inputs and I've got my outputs, if I can find my wires. Talk amongst yourselves while I'm doing this here. So much easier when the camera's not rolling. By the way, if you're watching this, know that this was the best take of all of them. The other ones didn't turn out so good. So you're getting the best of the whole deal here. There we go. All right, now we've got, I'm going to just turn this down here, make this a little more palatable, and I'm going to flip over to the table view. And there we go. So what I've got is I've got my Paul in a red shirt, Paul in a green shirt, Paul in a blue shirt, um, RGB potentiometers from the Raspberry Pi kit. And I've got 3 individual red, green, and blue LEDs. And now I can actually adjust. See, if I turn this LED, I can make the blue blink faster. So the blue is blinking at its own speed. The red and green are unaffected. I can turn green so fast that it's almost solid. And then red I'll actually turn so it's all solid. And we can see that all 3 of these are independently controlled, independent potentiometers, and they all have their own blink rate. So let's take a look at the code really quickly. I know this video is getting long. I'll try to wrap up here if I can. And what I'm looking at is I'm setting up my input pins and output pins. I'm setting up a delay timer for each of the LEDs. And I'm setting up a previous millis for each of the LEDs. I'm also setting up a state, so false, true for each of the LEDs to blink them on and off. Come through here, do the setup, and now you notice again, the first thing I do is I read the current timestamp in millis. I'm going to read in the value of all 3 potentiometers into their 3 different values, invert all 3 of them, and now I have 3 if stanzas, so each LED is going to get its own treatment here. I'm going to check the current timestamp against the red previous and its delay time. And again, if the delay time hasn't expired, we're just going to keep going. If it has expired, we're going to invert the value and reset the previous millis counter. Do the same for green, do the same for blue. So each has an individual timer, each has an individual counter, each has an individual stamp on it, or a state, I should say. And then we write out the state every time through the loop. So again, if I'm slowing this down, so if I were using delay, and here, I'll go back to the table view. If I was using delay and I had to slow the LED down, every time I slowed this blue LED down, it would affect the other 2. But because I'm using these millis loops and each individual LED has its own timer, the potentiometers for each LED don't affect each other. So this is the value of using millis loops inside of Arduino. So now you're probably wondering, okay, that's great, but what in the world does that have to do with joysticks and Raspberry Pi? Well, that's for my next video. Stay tuned for lesson number 3, where I wrap up the homework for lesson 18. We're going to take what we just learned in the Arduino world using millis, and we're going to apply it to Pi. And I hope you enjoy this lesson. Please hit like and subscribe below, and be sure to stay tuned for my final video on lesson 18, non-homework solution for TopTechBoy. I'm Brian from Simply Brian Enterprises, and thank you for watching.